Problem 5. Lose all scripted responses, improvisation only. Let finite be the language of encodings M, where M is a Turing machine and the language of M is finite. Let total be the language of encodings of M, where M is a Turing machine which halts on all inputs. What we want to show in this problem is that total reduces to finite. Okay, so what does this mean exactly? It means that if we assume we have some decider for finite, let's say it's called M finite, we can somehow use this as a subroutine to decide total, specifically by creating something called M total, which decides total. Okay. Now, before we get into the details of what this reduction is going to look like, let's just go over what the general strategy should be. So we want to show that we can create some decider M total, again, assuming that we have one for a finite. It's going to take in some input encoding M, where M is a Turing machine. So before we get into the details, let's just go through the definitions on the right side, and this is where our proof of correctness is going to be. If M is in total, simply by definition, it means that M of Z will always halt. No matter what input string Z we give it, M is going to halt. And similarly, if M is not in total, then M of Z will loop for some string Z. We don't necessarily know what Z is going to be, but we know that there has to exist some such string which will cause M to loop. Okay, now we're going to create this decider by assuming that we have a decider for finite. So what we'll need to do is eventually pass in some helper Turing machine that we create into the decider for finite, and hopefully this will tell us if M is total. So let's just go ahead and create this Turing machine, M help. And at the end, we're just going to run M finite on this encoding of M help. I would encourage you to pause the video right now and see if you can fill in the details to make this work. Okay, so now let's take a moment and go through the construction. What we're going to do is first of all notice that what we're running in M help is not actually running in M total. We're creating a function M help, we're defining it inside M total, but we're not actually running the code. We're just saying this is what it would do if it ran on X. So now what we're going to do inside the body of M help is we're going to consider every string Z where Z is less than or equal to X. Now, since it doesn't really make sense, this doesn't really type check, we're going to specify that this is called a length lex order. And all it means is that we're going to order the strings in such a way that all of the strings will show up. And this particular order, the length lex order, is going to start with the empty string and then start increasing lengths. So we'll go to all length 1 strings and simply put them in alphabetical order. Right? So we'll start with 0 and then 1, and then we'll go to length 2 strings and consider them all in alphabetical order. So this gives us a way to talk about a string being less than or equal to another string. Okay. Now what we're going to do for each of these Z's is we're going to run our input M on Z. And at the very end of this for loop, we're just going to go ahead and accept. Okay, so what exactly is going on here? Well, let's just simply go through the cases. Let's say the input M is total, which means that M of Z always halts. So notice what's going on inside the for loop for M help. If we were to run M help on some string X, we would run a finite number of iterations of this for loop, and each one would be guaranteed to halt. So what that means is that M help will always accept if we're assuming that M of Z always halts. So what does this mean? It means that the language of M help, this helper function that we're given, is going to be infinite. In fact, it's going to be all of sigma star. And what that means is that the result M help is not infinite. So maybe you see what the problem of this is. We're actually returning M finite called on the encoding of M help, where in fact we should be returning the negation of this quantity, because we know that it's going to be infinite if M is total. But that's an easy fix. So I think the bulk of this problem is understanding why it works in the opposite case. What happens if M is not total? What happens if there is some Z which causes M to loop? Well, now let's take a look at the for loop. Let's say that we're given some X for M help, and it's bigger than this Z, which causes M of Z to loop. Then when we're going from the start, empty string 0, 1, 0, 0, etc., we'll eventually reach this Z where M of Z loops. So what happens is if we have some string X, which is at least as big as Z in this order, M of help will loop forever. Notice what happens. The language of mHelp has to be finite. Why? Because it can't accept anything bigger than z. And z is some finite string, and in particular, there are only a finite number of things that are smaller than z in this lexicographic order. So it turns out that in this case, the encoding of mHelp is in the language finite, and that's all there is to it.